Okay, so today we're going to talk about probabilities and percentiles in a normal distribution. And for those of you who completed Algebra 2, you looking at this chart here, this picture of the normal distribution with the percentages filled in, and you probably recognize it because you did some problems with that last year. But the problems you do this year are a little more sophisticated, and you'll see. So anyway, we have two questions we plan to answer. Number one, how can we use what we know about the normal distribution to answer questions about percentiles and probabilities? And number two, how can we use a normal distribution area chart and z-scores to answer questions about percentiles and probabilities? Let's start with that first question. It's a little bit easier to answer. We'll consider an example. So let's consider SAT verbal scores. And this is just made up, but we'll use it anyway. Each year, the College Board publishes the mean SAT score and standard deviation for the students taking the test. SAT scores are normally distributed. Assume for a group of students that the mean SAT score was 500 with a standard deviation of approximately 100 points. Find the score that is one standard deviation above the mean. This is simply telling us to take the mean and add a standard deviation. So the mean is 500 plus the standard deviation of 100 is 600. Find the score that is one standard deviation below the mean. It's important in these questions to pay attention to direction, the words above and below, telling us which way to head. In this case, they want us to do mu minus a standard deviation. That's 500 minus 100 is 400. Okay. So turns out we could do a lot more than that if we refer to this chart that we saw back in Algebra 2. Now, for some students taking the course, they haven't seen this chart before. This is what we're going to use. A couple of comments just so you're aware of it. The mean always goes in the middle, so this 0 here in the center of the chart means that we're 0 standard deviations away from the mean. So mu goes right in the center of that chart. In our case, for this group of students, mu is 500. For 1, we look to the right, you'll see a 1 at the bottom of the chart. That means that we're 1 standard deviation above the mean, or mu plus sigma, which we'd already computed before, be 600. And then in a similar fashion, this negative 1 means mu minus sigma, or, as we computed earlier, 400. So now let's consider how we would answer this question number 2. Approximately what percentage would expect it to be score between 400 and 600? Well, it turns out it's pretty easy to do if you have this chart. Just look back here. Here's the score of 400. We trace that up the curve. Here's the score of 600. We trace that up. And all we have to do is add the percents in between here. So 19.1 plus 19.1 is 38.2 plus another 30 gives us a total of 68.2%. But we could ask about other intervals. So what about the percentage of students who score between 500 and 550? So again, we'll go back to our chart and mark that off. So 500 is right in the middle. 550 is not a full standard deviation away. It's actually half a standard deviation away. So 550 would correspond to this number. How do I know that? Because the standard deviation was 100, so half of the standard deviation would be 50. When I add that to the 500, I get 550. So if we just want the percent of students between 550 and 500, then we just want the area between those two green vertical lines. And we know that to be 19.1. Okay, how about the percent of kids above 750? I'll go back to this chart one more time. 750. Now we might have to think for a little bit. How many standard deviations are we away from the mean? Well, we can do that. First off, if we subtract off the mean, we get 250, which means we're 250 above the mean. Well, 250 divided by the standard deviation of 100 is 2.5. So a score of 750 is 2.5 standard deviations above the mean. That's all the way out here. You can circle that 2.5. And they want to know the probability that a student scored higher than that. So what we do is we draw a little vertical line, shade this tail, and we have to add 0.5% plus 0.1%, which gives us 0.6%. A very rare occurrence, according to this information. Well, for those of you who've taken the SAT, you know that when you get your scores back, or even the PSAT, often in your results, they'll cite a percentile. And they'll say something like, you scored at the 92nd percentile, which you know means the following. Scoring at the 92nd percentile means you scored better than or equal to 92% of all the students who took the test on that day. So what we're asking here is that if we got a score of 500 on this SAT, in this made-up example, what percentile would you be at? Well, we go back to our chart. We know that 500 is located at the middle of the distribution, which is the 50th percentile. That didn't take too much work. Now, 600, we know is one standard deviation above the mean, mu plus sigma. So now we need to ask ourselves, what percent of the observations are less than or equal to the mean plus one standard deviation? And again, we can go back to the chart to do that. Chart's getting a little busy, but we can still make it work. If we look at one standard deviation above the mean, we draw a blue vertical line there. If we're interested in what percentile we're at, what we need to do is add the area to the left of that point. Now, sometimes, this is where you might want to be a little bit clever. You can do the following. There's a lot of different numbers if you look at all the blue region. So what are some options? One thing you could do is know that the area under the whole curve is 100%. We could do 100% minus things that are above it. 9.2 minus 4.4 minus 1.7 minus 0.5 minus 0.1 and get an answer. Or you can do something else. Like, for example, we know that the area from the mean located at the center of the distribution over the area to the left of that point would be 50%. And all we want to do is add this extra 19.1 and this extra 15. And if we add those together, then we get an answer. So if we do that, we get an answer of 84.1%. So we're at the 84.1st percentile. Okay, the last question is asking us to consider what percentile we're at if we scored a 450. So let's go back to that normal distribution. 450 is 50 below the mean. Get a difference of 50. If we do 50 divided by 100, we get half a standard deviation. So we're half a standard deviation below the mean. What we can do is go to negative 0.5 on the bottom of the x-axis there, draw a vertical line up, and shade all the area to the left. And that's the area we really want. And according to my calculations, I'm getting 30.9 percentile. Okay, all these problems were carefully designed. Questions 1, 2, and 3 on this page were carefully designed so that the numbers you got landed either on one standard deviation of the mean, or half a standard deviation away from the mean, or 2.5 standard deviations away from the mean. But we do have to worry about what happens if someone scores in a different number. And that sort of leads us into our second question of the day. What do we do when an observation does not lie 1 or 2 or 1.5 standard deviations away from the mean? So to answer this question, we're going to consider the following example. So what percentile is Becky at if she scored a 730 on the SAT verbal? Well, if we draw our normal distribution, we know that 500 is in the middle. Mu equals 500. And we know that every standard deviation above is 100 more. So mu plus 1 standard deviation is 600. Mu plus 2 standard deviations is 700. And mu plus 3 standard deviations is 800. Well, we know the half standard deviation marks occur at 550, 650, and 750. But 730 doesn't land on 750 or 700. So we're going to have to change what we're doing. You could certainly take a guess at where it is, but I'd like to be more precise than that. So first off, I'm going to shade the desired area. If we're talking about a percentile, we're saying what percent of people did Becky score equal to or greater than on that day of the test. And that can be represented by all the area that you see here. Okay. The next step in solving a problem like this is find the z-score. Let's find how many standard deviations Becky is away from the mean. So to do that, we do z equals x minus mu over sigma. Or this means the observation minus the mean divided by the standard deviation. So in our case, the observation is 730, the mean is 500, and the standard deviation is 100. We subtract those things, we get 230 over 100, which is 2.3. The meaning of that 2.3 is as follows. Becky's score of 730 lies 2.3 standard deviations above the mean. So what I'd like to know is what that means in terms of the area to the left of her score. And to do that, or to answer a question like that, we need a special chart called a Z chart. Here's what it might look like. It's located in the front pages of your book. It's a little small font here. But you'll notice on the left, there's a column on the left here titled Z, and you can see all these numbers that are all negative. Those are all Z-scores and negative Z-scores, none of which apply to Rebecca because she got a 2.3. So we'll go to the next page. And we'll notice here's the second side of that normal chart. And if we look down, we can find the number 2.3 standard deviations above the mean. And if we look in the first column, you'll notice the first column title is 0.00. You would use the other title, the other columns like 0.01 or 0.02 if you had a z-score that were something different. Maybe you had a z-score that was 2.33. Then what you'd want to do is 2.33, you'd start in the 2.3 row, you'd go across, and so you got the column that had a 0.03 at the top, and you'd be interested in that number. That's not what we're interested in here. We're interested in 2.3 exactly, so 2.300, this number circled in green, is our answer. And what this chart gives us is it gives us the percentile that goes with that z-score. So the answer to this question is simply that number that we just had here, which is 0.98928. So the answer to this question is 0.98928. Or if you want to write it as a percent, you can write it the 98.9th percentile. That's pretty good. So here's another question we might want to know. We might say that we know in a certain class in school or something that all the students in that school scored between 420 and 670. And maybe we want to know, is that kind of what we expected? So the question I'm asking is, what percent of students score between a 420 and a 670? And this is where we can start to be a little more creative about how we use our Z-chart. First step, always, draw a picture of the area you desire. You should always do this. It decreases your chances of making an error. So this is my poorly drawn normal distribution. I'm sorry for that. Okay, we know the standard deviation in this case to be 100. So we can mark off some important numbers, 400, 300, 200, and then 600, 700, 800. And we want someone to score between 420 and 670. So 420 is going to be somewhere between 400 and 500, but closer to 400, so I'll make it right there. That's going to be 420. I'll draw a vertical line. And 670 will be a little closer to 700 than it is to 600. So we'll do this and draw a line. And here is the desired area. Now, what do we know about our Z-chart? Well, we just learned that our Z-chart only gives us percentiles. So if I take a minute and look and go calculate the Z-score for 420, let's do that. Z equals 420 minus 500 over 100, or negative 80 over 100, or negative 0.8. We can go look that number up in our Z-chart. So let's do that. So here we go. We look down the Z column, and here is negative 0.8 right here. And it was not negative 0.81 or 0.87 or anything like that. It was just negative 0.8. So we'll look in that first column. And I'll circle it in green again. There is the area we get, 0.21186. And what we have to remember is that's a percentile area. So that's the area less than or equal to negative 0.8 standard deviations below the mean. So when we go back to our chart, or our picture we drew, we have to know where to place that area. Remember, that area is actually to the left of this z-score of negative 0.8. So in here we put 0.211, bear with me for a second, 86. So that's the area to the left. Okay, so how can we get this desired green area we want? Well, we can certainly go calculate another z-score. We could go get the z-score for 670. So we can say z equals 670 minus 500 over 100. And if we do that, we get 170 over 100, or 1.7 standard deviations above the mean. So let's go back to the chart and look up that area. So we'll look at the positive z-scores. Here it is. Here's the 1.70. Here's the area to the left, 0.95543. And here's where we run into just a little bit of trouble. I think we can think it through and solve it. What we know is that if we're going to shade this, attempt to draw this, I'm going to look at all that stuff. That if we look at that area, drawn in red, that area is what we said earlier, is 0.95543. 0.95543. Okay, so I think we're ready now. If we look carefully, the 0.95543 includes the area from 670 over here, and then all the area to the left. And then if we look at where 420 hits the x-axis and the z-score of negative 0.8, we know the area to the left of that point is 0.21186. So you realize that this 0.95543 actually includes the 0.21186. So to get the desired green area that we want, all we need to do is subtract those. So the answer to our question is 0.95543 minus 0.21186, which equals 0.743 approximately. So we can say that in this distribution, approximately 74% of the students scored between a 420 and a 670. Okay, how else can we use the normal distribution to sort of help us answer some interesting questions? All right, so our subject, Becky, is not as strong in math, and she really wants to make it to at least the 90th percentile. So what score does she need to get if the mean SAT math score is a 480 and the standard deviation is a 110? Okay, so we know what the distribution looks like. We can draw a sketch of it. We could put 480, mu equals 480 in the middle. We can say that the standard deviation is 110. And so we can start marking off some important numbers. Like, for example, we add 110 to this, we get to 590. So that's mu plus 1 sigma. If we add 2 standard deviations to it, so mu plus 2 standard deviations, we add another 110 to that, that's going to be 700. And then 810. And then we can subtract. And if we subtract here, we would get 370 and 260. Okay. Now, Becky wants to score at least the 90th percentile. Now, without doing too much work, we can kind of figure out where that would have to be. Remember, our z-score gives us the percentile, or z-chart, that is. So I'm going to go back there. And what I have to realize now is that I actually don't know what the z-score is. But I do know what area that I want. I want to catch the 90th percentile. So what I'm going to do is look through this chart and find an area as close as possible to that. So if I look carefully, I look over here, look where the green pen is. I'll use blue, different color. I got a 0.89973, and then next to that, I have a 0.90147. Okay? Now this is a sort of an approximation. If I look at these two numbers, the 0.89973 is closer to 90%. So what is this telling me? See, Rebecca or Becky wanted to be at the 90th percentile. What that means is that she needs to score 1.28 standard deviations above the mean to get to the 90th percentile. So this is an example how you can use the normal distribution in reverse. So what we want to say for Rebecca is she wants her z-score to equal 1.28. Now, if we give it some thought, we realize we have all the information we need. We can say, use our z-score formula, which is z equals x minus mu over sigma. We can say that 1.28 equals x, which is unknown, minus the mean of 480 over the standard deviation of 110. So this is a problem that is solvable with basic algebra. First thing we could do if we want, cross multiply or multiply through by 110, however you want to say it. So 1.28 times 110 equals x minus 480. That means that x has to equal 480 plus 1.28 times 110. And you can see the format of this. We knew Rebecca or Becky wanted to get 1.28 standard deviations above the mean. Well, here's the mean. The above part is the plus. Here's the standard deviation, the number of standard deviations she wanted to be, 1.28 standard deviations above. And we're multiplying that by what the standard deviation is. So if you do this, we get an answer of about 621. So she would need to score 620 or higher to make it into the 90th percentile, scoring the way she wanted to. So this concludes your introduction on how to use z-scores and a z-chart to answer questions about the normal distribution and find probabilities and percentiles. Tomorrow, when you come to class, be prepared to answer more involved questions related to these things. See you then.